Welcome to the podcast. This is Mr. White.
Mr. Johnson.
And today I'm going to talk about making waves. So in the investigation, we did a few things. Let's see. We took some springs and we made some waves that looked like this. And we took some springs and we made some waves that looked like this. And what we don't realize, of course, is that these two things are actually very, very closely related.
Right.
So what we're trying to refer to, we're trying to get back to sound and light. And any thoughts about which of these waves is like sound and which of these waves is like light? It's an either-or thing.
Well, I would think that, if you think about sound, you think about like vibrations and meaning it to be the one on the bottom. Because it's like it's traveling through air and all of a sudden it gets picked up by something and vibrates faster and then keeps moving.
Right. And that's exactly it, too. So the sound wave is just that. It's all of this, the sound information causes the air to vibrate in front of it until it hits the next air particle, until it hits the next air particle, etc. This is called a longitudinal wave. And what's happening is the disturbance is parallel to the wave motion. So if the wave is moving to the right, then the disturbance was also
moving to the right.
Okay, so that is sound. We're able to do that with our springs. That's why we use springs or slinkies, by the way, because you're able to smash them together or stretch them out and actually see this. This, on the other hand, is light. And this has a different name altogether. This is called a transverse wave. So in the transverse wave, the wave itself is moving to the right, but the disturbance is not moving to the right. The disturbance is moving
Up and down.
Up and down. And so there's a 90-degree angle there that takes place. So the disturbance is perpendicular to the wave motion. So light is a transverse wave. Other waves that are transverse, water waves qualify. The sound wave is longitudinal. We'll have to look it up or put it up on the screen. I can't remember off the top of my head. It's either the P wave or the S wave in an earthquake is also longitudinal. One of them is transverse, the other one is longitudinal. But there are earthquake waves that do this, and I believe they're the ones that are filled with energy that actually knock buildings down and destroy bridges and things like that.
Because of the vibration.
Because of the vibrations that it's causing. So we got to investigate that a little bit. And so this is one distinction we can make between waves. Another distinction we can make is pulse versus periodic. And in class, at least I kept asking my students, are you supposed to be generating a pulse, or are you supposed to be creating an oscillation? What do you think the difference is there?
Well, pulse is you do something initially and it sends a wave out forward. An oscillation is where it goes up and then it comes back down and it does the same thing.
Okay, so a single event is a pulse, and a repeated event can cause a periodic wave. It's really just that simple. So if you were to move the spring and let the spring go once, you created a pulse wave. If you were to shake the spring back and forth repeatedly, that would be a periodic event. So there's one distinction. Another kind of distinction between waves. Let's see, we've done transverse and longitudinal. We've done pulse and periodic. I'm not sure if this one is covered in the text, but there's mechanical and there's non-mechanical. So a mechanical wave is, like for example, sound is a mechanical wave. Needs a medium. So like sound needs matter. Air, water, solid, doesn't matter. Water waves need water.
Right.
A non-mechanical wave does not need a medium.
It just travels.
Right. And so a good example of this would be what?
Light.
Light. Light's a perfect example of a non-mechanical wave. So we go to Star Wars. We could go with a lot of episodes here. How about Star Wars episode...
Well, we have to go to a newer one because they've seen a newer one.
No, we can't. We have to go with episode 6.
Oh, Jedi. Oh,
Return of the Jedi.
All
There's
right.
this thing in Star Wars called the Death Star. And it kind of looks like a moon. And it blows up. And if I remember right, they show this huge pulse of light that comes out of it as it explodes. And my question is, would you see an explosion in space?
Yes.
Because it's light.
Right.
Would you hear an explosion in space?
No.
Because there's no
air in a vacuum.
Yeah, there's nothing. There's nothing for the sound wave to travel through. So,
But now you're going to have those traditionalists of the movie. Well, what about when the pulse hits their ship?
no. Because the sound could never escape the Death Star because there was nothing for it to go through.
So then the sound of the exploding Death Star you won't hear, but you do hear the pulse on the ship vibrating it, making
Correct.
that sound.
But you're not hearing the sound of the explosion. If you were in the Death Star, because there's air and matter all around you, you would hear it exploding momentarily.
And it'd be the last thing you heard.
It would be, yes. Right? But in the ship, as you feel the ship vibrate, that would be from the energy of the explosion. It would not be from the sound of the explosion. It's always good to get a little Star Wars into our podcast.
Well, now, we won't go any further. I was going to say, what if you're in the Falcon and you're going right through as it explodes?
If you were to encounter the material of the Death Star, yes. But that would be bad in other ways.
We're getting too nerdy.
A little too. We've nerded this up enough.
We just ruined the movie for him.
Oh, yeah. No, this is the beginning. So, we've talked about all of this different stuff. There's also parts of a wave. And the reason why we have to do this is because we need to start speaking with the correct vocabulary.
Right.
So unfortunately, that means we're covering a lot in a short amount of time.
Mm-hmm.
So here we got a transverse wave.
Okay.
Because the disturbance is up and down, and the wave motion is to the right.
Mm-hmm.
The first thing we can label here is the distance from the middle position. Okay?
Where the wave crosses.
Where the wave crosses. So there's this imaginary line for every wave, and this distance from the center is called
The amplitude.
the amplitude. Amplitude. Okay? At the top, we would call this the crest. Maybe in math class you call it the peak.
Mm-hmm.
At the bottom, in science class, we're going to call it the trough. Maybe in math class you call it the valley.
I thought it was trial.
Yeah, either one will work. The distance of one full wave, okay? So it has to touch every point once, and it has to finish where it starts.
And start to repeat again.
And then it'll start to repeat again. That distance is called the wavelength. It's measured in meters, and it's the Greek letter lambda to define it. It's kind of like an upside down Y. Okay? The time it takes for one wavelength is called the period. It's measured in seconds and symbolized tragically with a capital T.
Right.
right? So these are just some of the different parts of the wave. And as you're going through the rest of your investigation, it might be a good idea to check some of this stuff out.
Now, I've often had students ask, now, the amplitude goes to the top of the crest. Is it still called the amplitude when it goes to the bottom of the trough?
That is a great question, and the answer to that question is yes. Okay, the amplitude is still the amplitude. It's going to be it's the maximum distance from, didn't label this, the equilibrium position. That dotted line is the equilibrium position. Good question.
Now, what about, we have wavelength and period. What about the number of waves?
So how often does the wave? So the period answers the question, how long does it take? Okay. The question, how often does an event occur, is answered by the question, frequency. So if this time from here to here were 1 second, then we would have 1 wave per second. That would be the frequency.
Okay.
If this time were from here to here were 1 second, we would have done half a wave in 1 second, so the frequency would be a half. Okay?
Okay.
If 1 second was way off on the other side of the screen, we could get lots of waves per second, and that would increase the frequency.
Okay.
With these parts come some equations for wave speed. Now, if you remember from the first semester, the wave speed or the speed was v, and it was some distance divided by some time.
Correct.
Okay. Do we have a distance up here somewhere?
Yep, wavelength.
Wavelength. Do we have some time up here somewhere?
Period.
Period. That's interesting. So I can also say that the speed is v is d over t, but the wave speed is v is the wavelength over the period capital T.
Now we change the symbols because when we're doing problems, you're not going to actually see distance or time. You're going to see wavelength and period.
Period. That's correct.
Okay.
Wave speed is also equal to the wavelength times the frequency. Because what we haven't yet talked about is that the period and the frequency are inversely related. So if, for example, what we would say here is, okay, this is half a wave in 1 second. Okay, so we go to our equation. Well, the period is 2 seconds, and we got half of a wave in there. So we just have to look at that and try not to get the two confused. Remember, frequency answers how often. Period answers the question, how long does the event take place? We've covered a lot. There's one more thing, I think.
And just to remember, too, the frequency's unit is hertz, but we're going to come back to that.
Yeah, right. So we talk about frequency. It's measured in hertz, named after a German physicist named Heinrich Hertz. He was one of the primary inventors of the radio, I think.
What's that?
The radio? Yeah, they might have a legit question there.
Yeah.
The last thing we have to talk about today is interference. Not the kind of interference that you get on your phone where you get static, although that is related. But we're just going to talk about general interference of a wave. So first semester we talked about matter.
Yep.
We talked about stuff running into other stuff. We talked about applying forces to objects. But the one common thing, we never once talked about it because it's impossible. Matter can't share space.
Correct.
So if two cars run into each other, one car hits the other car, the cars change their shape, but they do not occupy the same space at the same time. Interference means sharing space. So, if I have a wave pulse that's moving to the right, and I have another wave pulse that's moving to the left. If these were cars, they would meet somewhere in the middle, and they would crash to a stop. Okay? But because they're waves, and they can share space, sharing space at the same time. For one moment in time, that wave gets really big. This wave still exists and is moving to the right. This wave still exists and is moving to the left. And after the fact, The same thing is happening, but now they've passed each other. This can only happen in waves. This cannot happen in cars or any object that has matter, that has a volume and a mass. Okay? What if, and so this, by the way, this is called constructive interference. What if this were to happen? Any predictions about when they meet?
And when they meet, it's almost like one's on top, one's on bottom. It's going to be a cancellation.
Yeah. And if they're both the same size above and below equilibrium, they do in fact cancel each other out, something called destructive interference. And so what would happen after the fact would be this. So if they're on the same side of equilibrium, we have constructive. If they're on opposite sides of equilibrium, we have destructive interference. We could do the same thing on the bottom.
So now when we say that they cancel out, for a brief moment, their net wave is like null and void.
Correct, for one moment in time.
But they're still moving. It's just that at instant when they meet, it becomes void.
Yes.
And then they move past.
So when we talk about interference, the waves don't stop. That's a really important distinction to make. The waves don't stop. That is so important to clarify. They keep moving at exactly the same pace. They don't slow down or speed up either when they run into each other. They just pass through each other like the other one isn't even there.
Okay.
That's all that's all that's happening there. We drew pictures, by the way, so we drew transverse waves on the last several slides. All of this stuff, by the way, works for longitudinal waves. They have wavelengths, periods, frequencies. They undergo the property of interference.
And in fact, with the Slinky, you almost can actually see the disturbance happening when the two pulse, like if two people at one end send a pulse both ways, you see it. It almost looks like when they collide, it's like there's nothing there, and then you see the pulses come out.
That's it, yeah. And that's a really interesting phenomenon. Something you actually need to see several times because your eyes are trying to play a trick on you. So we covered a lot of vocabulary. You want to make sure that you distinguish which words are important
You still got that one slide you were drawing.
and which ones weren't.
Oh, this one. Okay. Oh, you were just drawing constructive on,
Yeah.
on the bottom. Oh, okay.
So we covered a lot of vocab. Let's make sure that you understand what we're talking about and that we start to use those words as we get through the investigations. It's going to make, if everyone's talking in the same language, it's going to make everybody a little easier to get along with in class.
And make sure you're writing down those formulas.
Formulas, units, all that stuff is still important. So the podcast is a little long, but a lot of material to cover. Signing off, this is Mr. White.
And Mr. Johnson.